We're talking about radioactive decay this week. And radioactive decay, we have to keep in mind that it is a naturally occurring process. Radioactive decay is not something that can be forced or messed with. We can manipulate what's happening, but then it's not called decay. Then we call it artificial transmutation because we're getting involved with it. So the biggest thing that we have to keep in mind with what's happening is it is a naturally occurring phenomenon. And with that, we have to keep in mind that we talk about in science how we observe things, and then we try and predict, and then we try to manipulate and do what we want with it. And so with radioactive decay, it's coming from the observation and the prediction. So it's been observed by scientists in how it's happening. It's been named and figured out, and then we can predict some things, but only to a certain extent, because with radioactive decay, it is a naturally occurring process. We don't have the control over it like we do over other things. So keep that in the back of your mind with what we're looking at for today. Now I'll go ahead and share the screen. Here we go. All right, so radioactivity is what we're talking about here. And let me do it like this so you can see it a little better. Maybe. There we go. So radioactivity was discovered almost by accident. Uranium is one that we'll talk about quite a bit. It can blacken a photographic plate even in the dark. And so what was realized is that, with a photographic plate, we don't really use stuff like this to the same extent anymore because everything's digital. But when it's exposed to light, you'll get different areas of light and dark on it. And what they found is that when uranium was present, that same phenomenon occurred. However, it wasn't light out. And so they realized that. And so this radiation that they found with that, and it's considered something radioactive. And so Marie and Pierre Curie discovered more radioactive elements. And so you hear about them. The bottom part of this says that they were called alpha, beta, and gamma rays from the first three letters of the Greek alphabet. And so we're going to focus. These are your three types of radiation that occur. And that's what we're going to talk about next, is how those work. This is really, really tiny. But I'm going to kind of talk through what's happening here. The types of particles are listed at the top. So you have alpha particles, beta particles, and gamma rays. With that, an alpha particle is always going to be 2 protons and 2 neutrons. It's essentially the nucleus of a helium atom. So you might see it written as He, you might see it written as alpha. Either way, it's 2 protons and 2 neutrons that we're talking about for an alpha particle. A beta particle is an electron created when the nucleus that decays. So one of the things that we're going to look at in what is happening here is that we can have the creation of an electron from the nucleus. And so that somewhat gets into some of the particle physics that we'll look at later when we get into quarks and leptons and things. But it is part of what happens with our beta decay. And so keep that in mind. It's not something, normally we're like, well, a proton's a proton, and a neutron's a neutron, electron's an electron. But as time has gone on, we've realized that there can be some shifting and creating as decay happens and as different nuclear reactions happen. And so when we're talking about a beta particle, we have an electron. It may also be, when we talk about beta positive decay, it can be an anti-electron, which we call a positron. And then we have gamma rays. Gamma rays they don't have a particle like a proton, neutron, or electron associated with it. It is going to be an electromagnetic wave that's emitted. And so what happens with that is it allows the nucleus of the atom to become more stable by lowering the amount of energy that is held within it. And so with that, it just settles down and is more stable. And we'll look at a graph in a little bit that shows that. So because alpha particles have a positive, have 2 protons in there, they have a positive 2 charge. Beta particles have a negative 1 charge. Again, unless they're beta positive, then they would have a positive 1 charge, and we'll talk about that when we get there. And then electromagnetic waves, because it's an gamma rays, because it is an electromagnetic wave, it doesn't have a charge associated with it. If we go down and look at the mass, and some of this, if you think this through, it's like, oh yeah, that makes sense because of how it's structured. So the mass is high compared with betas because it is 2 protons and 2 neutrons compared to the mass of an electron. Beta has a really low mass, and gamma rays don't have a mass. Speed is the speed of these when it's emitted. The alpha particles are up to 1/10 of the speed of light. Beta particles are up to 90% of the speed of light, and gamma particles are at the speed of light because it's an electromagnetic wave. Again, think about that. Alpha particles have a really large mass, so comparatively, they'll be traveling much slower. Ionizing effect. Ionizing effect means the ability to kind of knock off different parts of another bond, and to be able to knock off electrons from those other from another substance. And so we'll talk about ionizing in a little bit later. This is where we kind of get into things like how it is bad for your body if you're around radiation, because of what it does to kind of the structure of what you have. So with the alpha particles, it has a really strong ionizing effect. It can get in there and make some damage. Beta particles, it's not as strong, and gamma rays, it's very weak. Still is affecting, but not as strong. But then look at the penetrating effect. It's not, so with alpha particles, they're really big. And it says they're not very penetrating, stopped by a thick sheet of paper or by skin or by a few centimeters of air. So the alpha particles are really, really big. They're not moving quite as fast. And so if anything gets in their way, it's going to slow it down pretty quickly. So while it can have really strong ionizing effect, it doesn't go very far. Think about it. A few centimeters of air is just a little bit. And so it goes very, very little when it's released, but what it encounters, it can mess up pretty good. Beta particles don't have as strong of an ionizing effect because they're a lot smaller and they don't have as much mass. But they can still be, so they can penetrate farther. They can get farther through a substance, but they'll be stopped by a few millimeters of aluminum or other metal. And so when you have people who try and put, they try and make their aluminum houses and stuff and try and put aluminum on their windows, in kind of thought of space radiation, this is what they're trying to block out here. Gamma rays do not ionize as much comparatively. They still do have ionizing abilities, but it's not as much. However, they never are completely stopped. Through lead, thick concrete, that stuff will reduce it quite a bit, but it's never completely gone. And so even though the ionizing effect isn't very strong, it can go really far and can affect a whole lot of things. And so that's sort of the balance between those two things, between how much it can ionize and then how far that can go. And then the effects on the fields. So if you have an electric field or a magnetic field and you have this particle moving through it, how is it affected? And so you'll have, and we'll look at a slide that shows this in a little bit, but if you have an alpha particle, it has 2 positive charges. And so as that's moving, it will interact with the magnetic field and with an electric field. Beta particles have a charge as well, so they will also be deflected by electric and magnetic fields. And then a gamma ray doesn't have a charge with it, and so it will not interact with a magnetic or electric field. And some of the things that we look at in when we talk about the bubble chamber in a little bit, you'll see kind of how that plays out with what you have. If you have this diagram shows how different types are affected by a magnetic field. And so let's say you have this magnetic field that's created as in the diagram, and you can see if you have particles moving through from the left to the right, they behave in different ways. So the gamma moves through because it doesn't have a charge associated with it. The alpha has a positive charge. And so if we use our right hand rule and we put our fingers in line from north to south where the arrows are pointing for the field, and if we put our thumb in the direction of the positive particle, then you'll have your push up that is showing the alpha particle moving up off of the path that it was originally on. It has a lot of mass, so it's not going to be shifted greatly. It'll be moved up, but not in a giant way. If you think about the beta particle, now if I have it set up, my fingers are in the direction of the magnetic field. My thumb is in the direction of the motion, but because it is an electron, I'm going to flip that direction. And so my push would be down. And so the force that's created here is pushing down on that beta particle. And because the beta particle is small, it's deflected a lot more. And so these were some of the ways that scientists were able to start figuring out what's happening with these particles, what are they consisting of, and then based on how they're affected within a magnetic field here. And so keep this in mind and how these can be affected as they're going through here. This is the same stuff that I just talked about it. Ionizing properties. This is kind of what happens in the way of knocking electrons off of them and other things. So alpha particles, beta particles, and X-ray photons are all even as we talk about them comparatively and we say, oh, this one isn't as much as this one, they still carry a lot of energy with them. And so we frequently talk about this as an electron volt. And 1 joule is 6.24 times 10 to the 18th electron volts. Remember that 1 electron volt is 1.60 times 10 to the negative 19th joules. And so it ends up being the elementary charge for that. And we talked about that before. Typically, your kinetic energy of a single alpha particle is about 6 million electron volts. And so we write that as capital M for mega and then EV for electron volts, mega electron volts. And what happens is radiation ionizes the molecules by knocking electrons off of them. And so then the energy from the radiation the energy transferred from the radiation to the material. And so the other thing that happens if we talk about the way of how the ionizing properties work within covalent bonds is because it does that. One of those covalent bonds, or those electrons are holding those covalent bonds together, are holding that they're being shared by your nuclei there. And so what happens when you do that, it knocks off in a healthy cell, it knocks off one of those covalent bonds and changes the structure of that molecule. And so then when that starts now it's mutated, and if it starts to reproduce, then you have this mutated cell that's reproducing, and that's where it's bad. And when you're talking about radiation in the way of like cancer treatment, essentially they're going in and knocking out those covalent bonds of the cancer, and it allows that to break up and then to not continue to mutate. And so it can get in there and it destroys what's happening. So ionizing properties can be used for good or for not so good. When we're talking about like an atomic bomb, those ionizing properties are sent out recklessly. And when we're talking about medical treatments, those ionizing properties are being used to destroy the bad stuff. And so it's just sort of that balance in what we're using with each of these. When we talk about our ionizing properties here, an alpha particle goes through there. Let's say we have some air. There's not a whole lot that's going on here. It knocks off some, and when we're just talking about air, it's just going to be knocking off some of the electrons, knocks off some electrons in a short distance, and it has lost all of its energy. And so it's not anything that's going to be it'll encounter what it encounters, but it's not going to go very far. Because it's heavy, it doesn't go very far. It produces, and here it says about 1 times 10 to the 5th ion pairs per centimeter of its air path, but it doesn't go very far. Beta particle goes a lot farther. And so it doesn't go as much through there. Because it's moving faster, it's not going to spend a whole lot of time in one area. And so it knocks it out quickly and continues on its way. And so what that means is it's going to only produce times 10 to the 3rd ion pairs per centimeter. But it'll go an entire meter before it's absorbed. So it doesn't produce as much, but it goes farther. So overall, it can produce quite a bit. Gamma ray interacts weakly. And so it essentially will lose all of its energy in one big, quick event. However, it's not very probable that event happens quickly. And so it goes very far and can mess with a lot of stuff along the way. Quick diagram that looks at how these work. Paper will stop an alpha particle, but a beta and gamma would go through it. Aluminum will stop that beta particle, but a gamma will continue through it. And lead, the gamma continues through it. Not all of it, some of it it'll be lessened by having that. And so when you go and get an x-ray, like at the dentist, and they put the lead apron on you, that's to minimize the gamma rays from the x-ray machine. X-rays, it sounds funny. X-rays and gamma rays, we're on that continuum of the electromagnetic spectrum. And so x-rays, high level x-rays and low level gamma rays start to kind of interact, are sort of at a borderline between each other. And so when you have the gamma rays or the x-rays, lead will block both of those out. They can figure out radiation by using something called a Geiger-Müller counter. And what it is it takes in the surroundings there, and as it detects alpha, beta, or gamma rays, it makes an electrical spark. There's a really unique sound to it. It's sort of like this clicking. It's sort of like a click pop kind of combination. And as it does that, you're able to read it here, and you hear that, and it will tell you how much you have. What happens is you can have these on a large scale, you can have these on a small scale. When I worked at a different school, we had this science storeroom that was super sketchy. And I had a parent come to conferences, and his job was to detect radiation in like science or like plants where they're making things and stuff, manufacturing plants. And he accidentally had his Geiger counter on as he came up, and he came into conferences and he goes, "Hey, what's in that door over there?" I'm like, "Oh, that's the science storeroom." He goes, "Yeah, my Geiger counter just went nuts." And so that's kind of one of those things. It's like, "Oh, really?" So we then did go through and clean out a whole bunch. It had been there for years when we inherited it. And so it makes this kind of click that goes along, and what happens is the radiation gets in there, it sends a spark of electricity, and it causes that click that's happening here. It sets off, so it goes through the window. It's mica is the window that it is. Mica is a mineral that is a really thin, it's actually a really neat mineral. It peels off really thin. It's one of the things that I think would be fun to go to, like a mica mine and to see it, because it's just like these thin layers. It's just kind of look through it. It's almost cellophane like, but it's got more strength to it than what you would have for cellophane. So it goes through there. What it does, the reason it's a mica window there is because it allows the radiation to pass through that without any interference. And as it does that, it ionizes the gas inside, so it knocks off some of those electrons. As it does that, those electrons go, you have a high voltage spark across the gas then, and a pulse of current in the circuit. And that's what we hear with that. Beta particle or a burst of gamma radiation has the same effect. And so when it goes through here, it does that and it makes that pop, and then it'll either go to that pop. Sometimes they have a light, sometimes whatever. Most of the time it's connected to a sensor that'll give you a number. Cloud and bubble chamber is sort of how they were able to figure out what was going on with this. What they have with this is that the radiation from a radioactive source ionizes the cold air inside of that chamber. They have some alcohol in there that condenses on the ions of the air to form a tiny trail of white droplets across the path of that radiation. And so in sending that in, they were able to get some different things. Now look at the one on the left is alpha radiation. The middle one is beta radiation, and then gamma radiation. And you can see how the strength changes. The strength of those lines changes by the particle. Alpha particles are not moving as quickly, and they have a large mass. And so you can see that as it goes across, there's that limit to where it goes because it has already lost all of its energy. But because it ionizes a lot along the way, you get a really clear line there. The beta ones are lighter. You're not able to see them as much, but they go all the way to the edge. And then because they travel farther, they don't ionize as much. And then the gamma one, or the gamma radiation is just sort of a goofy look to it because it is traveling far, it's moving really quickly, and there's not as much of an effect to what's happening. All right, a little bit more about that. I want to talk about the stability graph. This is a graph that you will need to reproduce. There will be times when it'll show up and it'll say you need to draw this, you need to do this, you need to be able to talk about it. And so I'm going to talk through the graph and what's happening with it. And again, remember that these are things that are being observed. This is not something we can control. It's not something that we can do anything with in the way of radioactivity. And so this graph has a few different things. On the x-axis, we have the number of protons in the nucleus. On the y-axis, we have the number of neutrons in the nucleus. And what we're looking at is the balance between protons and neutrons that are formed in there. And depending on what that balance is will depend on A, if it's a possibility for that for that nucleus to even exist. And then B, if it is existing, what type of stability do you have with that? How long will it actually stay before it releases something? And so you have a dotted line that shows up on this graph, and it says N equals Z. And so N is your number of neutrons, Z is your number of protons, and that dotted line represents when you have equal number of protons and neutrons. If you look at the smaller number of protons, so things like carbon and oxygen and that sort of grouping, you have an equal number of protons and neutrons in there for the most part. It follows along that dotted line. As you start getting to the larger nuclei, you start steering a little bit away from that equal mark. And you'll have more neutrons than protons that are existing in your nucleus. The green section along that graph is where you'll have stable nuclei. Once it's in there, it's good. It's not going to release energy. It's not going to require any changes. It's going to be stable. If it is in that red area, and that's sort of, it's sort of a generalization. You may have something that's a tiny bit out of the red area. But if it's in that red area, then it can exist, but it's not going to stay. And that ability for it not to stay might be really fast, or it might be a considerable amount of time, but we know that in the end, it has the probability or the potential to decay, and it will. And so you have this, so again, the green is where it's stable, the red is where it's not stable, and then that N equals Z line is where it ends up being, where that proton and neutron numbers are equal there. So again, this is something you'll need to be real familiar with. Let's talk about stability for a minute. We have this strong nuclear force that holds the nucleons together, so protons and neutrons, but it's very short range. We also, remember, have the repulsive electric force between the protons, and so those can push apart. In a large nucleus, all the protons are repelling each other, but each nucleon only attracts its nearest neighbors. So you actually need some more neutrons to hold it together, so that you can have those nearest neighbors being held together by the strong force. Then on the second to last one there, it says that the more neutrons are needed, although adding too many can also cause instability. And we'll talk about that when we talk about fission a little bit. This last part here, an upper limit to the size of a stable nucleus, because all of the nuclides with Z bigger than 83 are unstable. So if you have more than 83 protons, you are going to have an unstable nucleus. When we talk about nuclides, we're essentially talking about the nucleus of the atom without the electrons on it. So what do these equations look like? We have 4 different types. Alpha particle is 2 protons and 2 neutrons. So it's written as helium or 4-2 alpha. I don't have a preference. I don't think the IB has a preference, but please note that you are paying attention to what's actually happening with these. So you know if it's 4-2 that you have an alpha particle with that. What happens is you have some atom, and it's going to, over time, it will release an alpha particle. When it releases an alpha particle, your nucleon number decreases by 4, proton number decreases by 2. Anytime you have your alpha decay, this is what's happening to that. Again, in chemistry, you talk about that an atom is an atom is an atom, and it just stays there, and whatever your protons in the nucleus, that's what determines it, and it's not going to change. Nuclear physics or nuclear chemistry both take a look at and say, no, it can change. It just kind of has a bigger process than what we have here. When we're talking about beta decay, beta emission looks like this. If we're talking about regular beta decay, which is a negative, which is an electron, so we say beta negative, there's so many layers to this. Your nucleon number stays the same, but you're adding a proton. So it means that one of your neutrons is actually changing into a proton. And in the process, you have an electron that's released. And then you have this other little symbol there that's a V with a line over it. It's called an antineutrino. Sorry, what? Okay, so here's the thing. A bunch of, we talk about conservation laws. And when we're looking at beta decay, several of the conservation laws were conserved, but some were not. One of them, I think, was momentum. Another one was energy. There's different pieces of that were not conserved. And so scientists had to look and say, okay, well, something else must be there. And so they did some different pieces that went along with that, like some different experiments to figure out what was going on. And we had a nuclear equation balances, energy and momentum are not conserved, and there has to be another particle. They called it the neutrino. There also exists with it an antineutrino. And essentially it says that the momentum and energy escape in a tiny particle. And they've done experiments to see this. They see it, they know it exists, but it's so tiny that it's still considered massless. They haven't been able to put a number to it. The mass of the overall mass doesn't change. They call it a neutrino, and for Italian that means little neutral one. And so, sometimes the thing that I love about talking about this stuff is sometimes it just sounds made up. And so physicists have to take and think like, okay, well, what actually happens here? And how do we do that? Okay, well, there has to be something else. What is it? Oh, it's little. Let's call it a neutrino. Cool. Let's do some experiments. Oh, look, we found it, sort of. But there's been enough experiments to identify and confirm the presence of this neutrino or antineutrino. The antineutrino accompanies the electron in beta decay. So when you have when you have beta negative, you'll have that negative charge on the electron, and that's accompanied by what we call this antineutrino. A neutrino accompanies the positron in beta decay. So when we have an electron type particle with a positive charge, we refer to that as a positron. That has a similar particle with it, but it's the neutrino instead of the antineutrino. When we talk in a few weeks about all of kind of the inner workings of protons, neutrons, and electrons and get into all of that stuff. We'll talk about particles and antiparticles. And the particles and antiparticles are exactly the same, except they have some different other properties are reversed in the antiparticle. And so the neutrino itself accompanies the positron, and the positron is the antiparticle of the electron. And the antineutrino, which is the antiparticle of the neutrino, accompanies the electron, which is just the particle. Follow that? It's kind of a mess. We'll keep at it. And so we talked about the anti piece of that. Neutrino has no electric charge, thought to have no mass, but more recent experiments suggest there might be a minimal mass smaller than the electron, but still not able to be quantified. It interacts very weakly with matter and is really hard to detect. Yes, and it does sound made up. So what happens with beta decay is if you have something that is, so think about that graph that we just had, and we had the green line in the middle and then the red around it. So this just focuses on the green part. If you have beta decay, regular beta negative decay, it loses a neutron and it gains a proton. So it moves down on the y-axis and it moves to the right on the x-axis. And in doing that, it brings it closer to that green line. If you have a beta positive, you have a proton turning into a neutron. So it moves to the left on your horizontal axis, and then it moves up on your vertical axis with your neutrons, again, bringing it closer to that green line. It won't naturally occur to move farther from the green line. When we're talking about naturally occurring, when something happens, when you have your decay, you will be moving closer to the green line. And so if you're starting above the green line, it would be beta decay to move it closer to the green line. When you're starting below the green line, it will be beta positive decay to move it closer to the green line. Gamma does not change the structure, but it becomes more stable because it reduces the energy of the nucleus. And there's another stability graph that we'll look at when we talk about fission and fusion. All right, we're getting there. Decay chains, a lot of times it won't just decay in one drop. It'll start as something, it'll decay to something else that is unstable. It'll decay to something else that is unstable. It'll decay to something else that is unstable until it gets to something that is stable enough to stay. And so you'll have this chain that goes from one piece to the next. In the practice problems that you'll be working on this week, you'll see that chain, and you'll actually do something with drawing that chain out for one example. A decay chain can look like this. There are different parts that end up being, that can be different. And so if you start up here at uranium and you're dropping to, you end up dropping down here with some alpha decay, and you're working through this. As this is happening, you might come to a point where you have, so alpha is going down like this. Beta is moving to the side. And so it could go alpha and then two betas. It could do one beta and alpha and another beta. It could do two betas and an alpha. There's different paths it can take, but it still gets down to the end of what it has and becomes more stable at the end of that decay chain. Half-life occurs with this. And so you don't have a set rate that continues like 10 per second or 15 per second. You just have, it'll drop half. You have a half-life. So how long does it take to get half of them decayed? You can't pinpoint and say this one's going to go next. But you can say that in this sample, it'll take this amount of time for it to be half. So if you start with 100, and let's say your half-life is a day, after one day you would have 50 of them left. In the next day, you wouldn't have all 50 of them go that's remaining. You'd go down to 25. And the next day, you'd go down to 12 or 13. And the next day, you'd go down to like 6. And you'd keep going down. And every half-life, you have half of it that goes. It is a spontaneous process. It is completely random. And there's not, you can't sit and pick one out, but there is a certain probability that it'll go within that half-life. Half of them will go, half of them will stay. And then it's half, half, half. And you're going to do a lab on this week involving M&Ms. If you could get your hands on some M&Ms, cool. Skittles work, a handful of coins works. So there are different ways to do it. And I'll show you that. I actually really like this lab. It does a good job of showing it, and it's pretty fun. I will put up a video that shows how to do it. And so if you talk about iodine 131, it's a radioactive isotope of iodine. And the half-life here is 8 days. So if it starts with 40 million undecayed nuclei, then after 8 days, we have 20 million left. 8 more days to 16 days, we've gone 20 and half to 10. And then 8 more days to 24 days, you've gone from 10 to 5. And so it keeps cutting in half as you go along. That's just what I just said. And half-life graphs look like this. You will need to be able to look at and be able to identify and talk about what's happening here. And so when we talk about this, you look at it, and if you go down halfway to half of your original number, you've gone over a certain amount. That's your half-life. If we're talking about what we had before, it'd be 8 days. You go down half again and another 8 days. You go down half again and another 8 days, half again, another 8 days. And so you can see these half-lives in here, and it's based on where you have half of that original sample, or the previous sample remaining. And so again, you'll do some practice on this week. We have this other of activity, and it's the average number of kind of releases that you have in there per second is called the activity. And the activity graph looks similar to the half-life graph. And so the activity here is different than the activity here because you have fewer undecayed nuclei remaining at this point. And so the activity graph is going to mirror the radioactivity graph. It's just using a different label on the y-axis there. It is a random process, so I will always look at it as a clean curve. It looks something more like this. And again, when you do your lab this week, you'll experience that part of it. I think that's it. Exponential decay is another way of looking at this. And then we'll get into talk about nuclear reactions next week. And just a little highlight, we're going to get to this E equals MC squared. So again, it's some really neat stuff. Holy moly, I just blew through a ton of stuff with that. And I know it's new to each of you. And so it's stuff that it can be a little bit goofy to think about. So 2 things. One, I'm going to put up that slideshow so you can take a look at it. This week, your focus is on radioactive decay. And you're going to be looking at that in the way of half-life graphs. You're going to look at that in the way of the simulation using the M&Ms. And you're going to look at that in the way of being able to predict based on what's already given, if you'll have alpha decay, beta decay, or if it tells you what type of decay, being able to use a nuclear equation to figure out what new nucleus you end with there. So again, while this stuff can be kind of mess with your brain a little bit, my hope is that we have it chunked in a way that it's approachable and you can work it through. And quite honestly, like as you do that, you'll be able to start seeing like, oh, I can do this. Yeah, this makes sense. Why it happens, all of the pieces surrounding it. There's a lot of, like, even in the scientific community, there's pieces we don't know about that. But being able to identify what's happening and be able to predict what's happening based on what we know is what we're going for. So you get to work with radioactive decay this week with safe things like M&Ms or coins or something. Just real quick on the M&M lab, what you'll do is you'll have the M&Ms in a cup and you'll pour them out, and any of them that don't have the M pointing up, you'll remove, you'll write that down, shake them up again, pour them out. Any of them without the M up, you remove, and you'll do that a bunch of times. So if you're not using M&Ms, as long as something is sort of circular shaped, so you have the equal probability of flipping on one side or the other, and it is different on one side, so you can tell you can identify quickly whether something's happening. You can use that. So like I said, if you have a penny jar at home and you use a bunch of pennies and do that, the lowest number you should have is 30. Usually kind of 50 to 100 gives you a good sampling to do what you need to do. So Have fun with that. Um, have an awesome weekend. Enjoy your extra day off. Work on, keep moving forward on your IAs. If you have questions on that, it doesn't have, don't wait to the rough draft discussion to have questions. So if there's something you're wondering about, shoot me an email. I'll get back to you and we'll figure it out. So I'll be on for a few more minutes if you have any questions. Other than that, have an excellent day and we will see you later. Bye-bye.